Hello everyone, hope you're doing well. This video, I'm going to show you how to work with a scratchANN. If you haven't watched the previous video, I suggest you to go to the previous videos and then watch this one, because this one I'm not going to cover the basics of this scratchANN. Previously I said mentioned that you need to know a little bit the basics of C programming, not the basics, because kind of you need to know memory management, pointers and stuff like that. And also you need to know the basics of artificial neural network, how they are formulated. And essentially after, if you read this book, it's going to tell you how to formulate, how to train, formulate the training the model, and also at the end, and having some examples, and then having an introduction, a section covering introduction to scratchANN, and then having some previously we covered a case study for energy efficiency dataset. This was the first video I uploaded on YouTube channel. Then we had another test case study on breast cancer dataset. Then this video we're gonna cover test case study on MNIST 784, which the dataset is larger and the model, training the model is a little bit more challenging. Let's go to GitHub. This is the GitHub repository that you can download all the codes, this open source library. Let me check. Okay, I'm recording. I always think that I'm not recording. Then previously we covered breast cancer energy efficiency. This time we're going to cover MNIST. I haven't uploaded the data here because the data was a little bit large. I didn't upload the file. You can use this Python code to fetch the data and then one hot encode the output, the target, which the target is a classification data, and then essentially saving the data in a text file like this, which has 784, where is it? 784 inputs, and because this is a classification data set, and we need to see, oh yeah, maybe I can just search it. For the dataset are actually images, and every image is going to be a number, and we need to say, okay, this image is representing 3, 4, 5, 6, 8, 9. So essentially we have 10 different classes. Every image is going to be something like this. We pass this image to the neural network, and the neural network is going to identify, is going to classify the inputs. This is the data set I have. This means I should create a neural network with 784 inputs. So this is 784 x1 to x784, and the output is going to be one neuron. If we don't encode that, one neuron identifying what is the class, and the class can be 0 or maybe I have this, or 1 or 2 and the rest. But I don't want to do that. After you encode the way I encoded the data, essentially the last layer is going to have 10 neurons, 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. And each one of these outputs is actually the probability of the class. So let's say this is class 0, And the last one is the class number 9, the different numbers 0 to 9. This is what I know from the data. I don't usually use softmax. Softmax, if you know the formulation of the softmax, there's some exponential, some division, and with all these divisions and exponentials, some precision is going to be lost. And if you have precision loss, it means you're losing some information. So instead of that, I'm going to say every activation function here is going to be a sigmoid. I don't want to normalize that, but this is the way I program that. In the future, if you like, you can say, okay, I'm going to do it with the sigmoid, with the softmax. But here in scratchANN, I didn't develop the softmax. I'm using the sigmoid. So this is so far what I know about the data. Download the data, and also you have a demo file. This means after you download the data, the rest of the files are exactly the same. The only thing you need to do, maybe I can create, open VS Code. This is the demo file for MNIST. The inputs are given here. You just need to change the make file so that instead of referencing to this source code, it's going to reference to demo MNIST. The inputs are given here. What I know based on the data is the first layer is going to have 784 neurons with no activation functions. It's the input layer. The last layer is going to have 10 neurons. And whatever I have in between, it's up to me. It's up to you how many hidden layers you want to have. Hidden layers. In this case, we have 128 neurons. I would call it L2, and 64 actually. 64 neurons here, which I call this L3. This is L1, and this is the L4. This is the architecture of the model I chose, and all these neurons are connected together. These are the basics. I don't want to cover them, but just all these neurons and multi-layer perceptron are connected together. Anyway, I'm going to use 80% of the data set to train the model. The batch size I'm picking is 64. This is the learning rate. I'm going to go for only 3 epochs. I'm going to print every 1 epoch. I can change it if I don't want to bother myself by printing. I can just remove this one. Not removing, I can just give it, let's say 4. And then if I give it 4, only the first one and the last one are going to be printed out. The data, the metrics, I want to measure the accuracy because this is a categorical type. This is a classification. This is the option I have to pick. You have 2 options. In the first video, we covered dataset called energy efficiency, where the outputs were we had 2 outputs, and each one of the outputs were continuous. And the second video I uploaded here for second training dataset, which was breast cancer dataset. It was a binary output. It was just one binary output. And now we are doing the MNIST, which is a categorical. I downloaded a file here. This is the file I have. I downloaded the data, and I want to shuffle the data. I want to always do that to make sure that the samples are uniformly distributed in a uniform way is distributed between train and test, and then standardization. I want to do that, but here I want to compare the results with what I have in MNIST. I set this to false, but technically I'm dividing every input, every one of the x values to 200 by 255. Why 255? In MNIST dataset, let me just, maybe I can show you to you. You already have it here, but you can, maybe I can open actually this one. This is good. Is there a picture here? Okay. Actually, it's not showing. Okay, you know what? Forget about that. Oh, okay, actually here, the pixels. If the pixel is white color, then the value is 0. If the pixel is written, something is written, the value is for this 2D. It's a 2D image, and every pixel is presented by a number from 0 to 255. It's the value is called the color is 0. The color is white. It's called 0. It's going to be equal to 0. And if the value is black, it's written something, then it's going to be the color is black, then the value is equal to 255. This means I have a 2D image again, something like this, and every pixel, this is going to be an integer number between 0 to 255. Okay, and some of the integers, especially in the corners, are quite close to, are going to be always 0. So the range of the changes for some of the inputs are going to be always 0. This is 280 by 280 pixel image. So 280 times 280. Oh, did I say 200? No, I'm sorry, 200. I said 200. I'm sorry. 28 times 28 is 784. These are the number of inputs I have. Every pixel is one input. Okay, this is the way I'm passing my inputs to my neural network. And what I want to do, I need to standardize the data, because again, some of the x values, if this is the way I design, I'm setting up my 784. This is the way I save the data here. Okay, so the file is a little bit large. It's going to take some time to open here. But anyway, some of these inputs, the range of the data is going to be changed. It's not going to be even changed. It's going to always become equal to 0. But some of the input values, they're going to have a range of 0 to 255. So the range is different from one x to another x. I need to standardize the data, but I'm using another method. I'm just dividing every x value by 255. I can use this as standardization method I have as well. Probably it's going to be even better, but I just want to keep it simple and divide it by 255. And then I'm going to save the model in my hard disk, my local computer. I don't want to waste hours of my time training a model and not being able to use it in the future. I want to save it, and I want in the future, if I want to be able to load the model, use the model, or retrain the model if it's necessary with a set of new settings or a new data set. That's why I'm going to pick a name that I want to save the model in text format. This is the way this scratchANN is written. I want to save it in my local machine. I'm going to show you how we can save and load and then retrain the model. One thing I guess I forgot to mention, that you have to use this code to download the data. The data is written in a format that every column is separated with one tab space. This is the way I wrote the program. If you want to change that, then you need to change the file called read data, because we're going to use this function to read the text file and save everything into a 2D array called data. So if you want to change this format, you need to change this one. You may want to read it with the data from an Excel file, then you need to just change this file. The rest is quite similar to the previous case studies we had. This is the way I'm setting the activation function. This means here, all this hidden layer is going to have tangent hyperbolic activation functions. Second one, I'm saying all these neurons, the second hidden layer, or the layer number 3 is going to have a tangent activation function. And for the last one, all of them are going to have a sigmoid activation function. Then I read the data, shuffle the data, and then I split the data into train and validation. Again, it's not technically validation, it's a test. It should be called test because we're not validating anything, we're just testing the model to see if it's working for the unseen data as well. I deallocate the memory for the 2D array I save the data into, because I split the data into train and validation. If it's not the best way to write this program, because I'm creating another copy of the data. In the future, if you want, you can change this one to make it more efficient. Scale standardization, this was false, it didn't happen. We passed the boolean to be false, but I'm dividing all the x values by 255. This is the same code. We're gonna compare the efficiency of scratchANN with the model we have on, or the same model we have on Python TensorFlow. I create the model, train the model, save the model on the local disk. I free up the memory because I don't want to have memory leak, and then I reload the model, which I saved. Again, this file name saved was model text file. I saved everything in a text format, save the weights and biases which I trained, and then I trained the model which I just loaded with the new settings. And I want to see if I can increase the efficiency, accuracy, or any metrics I want to improve. And then I free up the memory and free up the memory allocated for the given dataset. Anyway, let's for the data we read from a file, split it into train and validation, or in other words, test. So let's I guess I changed I changed the makefile as well. Let's compile the code, and then I'm using per computation with using 4 threads. I don't have more space because right now I have another application recording the screen that's already taking enough of my CPU. So let me just see. It's already almost 2 cores, almost 1 core of my CPU is taken only for this one. So I guess 4 threads should be fine. But anyway, let's run the program. Right now it's going to read the data. We have 70,000 samples, and training the model. Where you can see it's even 4 is too much. I should have changed this maybe to 2, I guess. 70,000 samples I have. The total number of the features are 794. 784 are the inputs, the pixels, and the other 10 is actually the outputs I have. The outputs are just giving you the outputs are these ones. So in total 10 outputs and 784 inputs. In total is going to be 794 feature I have. Then the data is shuffled, splitting data. 80% of the data is being used for training my model. Then validation, well, the rest, which is 20%. About the layers, in the first layer I have 784. Third layer I have 128 neurons. Second layer, I'm sorry, the third layer I have 64, and the last layer I have 10 neurons. The activation function, all the neurons, and the first one doesn't have any activation, doesn't have any weights or something, so the trainable parameters are going to be 0. The activation function is doesn't have any activation function neither. The number of parameters is to be trained in the first layer, first hidden layer, is, we talked about this one in the previous one. So previous layer here I had 784 outputs. This means every neuron is going to have 784 weights, and every neuron is going to have one bias, and the number of the trainable parameters in the whole layer is going to be time. So this is the number of parameters in every neuron times the number of neurons in this layer, which is 128. This is the way you calculate the number of trainable parameters. And all these neurons are going to have the activation function of tangent hyperbolic, as well as the second layer, second hidden layer, and the output layer is going to have only 10 neurons, this one, and all the activation functions, the activation function for all the neurons is sigmoid. The number of trainable parameters is 100,000, over 100,000, and then the batch size is 640, and the number of epochs is 3. The learning weight is 0.05. The matrix is categorical. You can see in the first epoch, the validation accuracy is, we're going to compute the train cost, we're going to compute the train accuracy, validation cost, and validation accuracy. You have to look it up on the internet how in a categorical function we calculate these parameters. And essentially, they didn't improve much. Let me just make, we need to run the model 3 times to make sure it's working. Oh, one thing I can do, I don't want to waste my time. Okay. So let's run the code again. So this part, running the data is from, reading the data is from here, then shuffling the data is from here, then splitting the data is from this function. Let me see. Okay, this is even worse. I guess I have to run it one more time. Maybe I can. And then, well, we didn't create the model, and after we created the model, we call the summary to see the summary of the model. Because this is even worse. Okay. Okay, let's just do it one more time. And just when you're testing your models, close other applications. Right now, this application is bothering the CPU, and we're not getting the. Okay. This one is actually better. The reason is you have 1,000 over 100,000 parameters needs to be initialized, and depending on how much the initialization is better, you might have it's a random function, and you might have different results. In another word, to initialize every parameter, I'm using a rand function, which this rand function is using libsodium library, which is highly efficient. Other functions, other randomizing randomized value creator is not going to be efficient as much as this libsodium. I really suggest you to use also this one. Anyway, this is the result I get. So after like 3 epochs, the initial one, the result was this one, and then after 2 more epochs, the result didn't improve much. I would suggest to stop here, not to overtrain and overfit on the data. So let's go back to this one. Creating the model, and then after you create the model, when you're training, when you call the training function, a bunch of settings are going to be printed, and for every epoch the efficiency is going to be computed, and then you save the model on the disk inside this file. So if I go here, I can see the weights and biases which I saved on my local disk. This is taking some time again because this software is taking a lot of my, although this is 100,000. Okay, this is quite probably large. It's not going to open. We're going to leave it like this. I saved everything. I deallocated the memory. I don't want to have memory leak. And then I reload the model. And then with a new setting, I change the learning rate. I lower the learning rate. And then for 4 more epochs, I'm going to train the model. And I'm going to see, okay, the accuracy increased a little bit more to 97%, but I won't bother myself with 1% retraining the model and taking the risk of overfitting. The cost also increased as well, like the cost was here and now the cost is here, but you never know, you might have overfitting. As long as these two values are quite close together, this cost with this cost and this accuracy with this accuracy, you may say, okay, you don't have much overfitting yet. Let me see. Okay, this is, go back to the previous videos to see the weights and biases, which is saved as model text file. Now we want to check the model we have here with the TensorFlow multi-layer perceptron model. Anyway, here I just wanted to know how many CPUs TensorFlow is going to use. It's going to use 4 threads, and then this is the way I standardize the data divided by 255. Again, you can call this standardization function, or you can just, for this specific data set, you can divide it by 200 because you know what's the range. Essentially, you're going to normalize the data to be between 0 and 1. The target is already encoded. Oh no, actually it's going to be 1 hot encoded here. Then I split the data. The default shuffling boolean here is true. Automatically it's going to be shuffled. We used 80% of the data for train. Here is using 20% for test. It's exactly the same. The number of the inputs, the number of the neurons in the first layer is 784, which the same as what we have, and then the next layer is 128, 64, and the next one is 10. And then for the activation function, this one is tangent, this one is tangent hyperbolic as well, and this last one is a sigmoid. And then scratchANN only has SG. In the future, if you would like to develop the model, you can develop more sophisticated optimization algorithm, specifically Atom. And in case if it's needed, if you don't have much data sample, but you're creating a model which might be relatively large, the number of the parameters you have to train is high, but the sample of the data is less, you need to go after more global optimization algorithms. Here it works, it's fine. but again, scratchANN doesn't have the other ones. You can develop it in the future if you want. Learning rate is 0.5, the same thing. 0.05, the same thing we have here. It's categorical. Again, the option we gave is categorical to measure the metrics. And the things I want to print is also plus the cost, which is the loss function. I want to also print out the accuracy. And I create this model, and then well, right now I already run the code. It's 93% accuracy. Let me say 93% accuracy. Quite close to what we have, 97%. Again, the difference is I implemented exactly the same thing. The reason is scratchANN probably working better than TensorFlow is just initialization, I believe, because the SGD algorithm is exactly the same thing I implemented. The number of the parameters is exactly the same, the number of trainable parameters. And I think the only advantage that scratchANN has to achieve a better accuracy is just using leap sodium to initialize the weights and biases. Anyway, maybe we can try it one more time. Let's see what we're gonna get. Yeah, it's the same. It doesn't, after 2 pokes, it doesn't improve much, so I would say this is already enough. And if I press this one again, it's going to retrain the model which was already trained for 3 epochs. It's not going to reinitialize the weights and biases. It's going to use the previously trained biases and weights, and then it's going to run the training for 3 more epochs. You can see this time when I run the code, it's going to start from the accuracy of 94. The accuracy is not low like the previous one because it's using the other model which was already trained. That's the purpose of saving the model on a scratchANN and reusing the model again. You can see the model which was already trained was loaded from the hard disk, and it was retrained for 4 more epochs, which again, it was not necessary. You could see already the model was kind of getting close to probably a local enough minimum. It's 90% accuracy. In another term, in another way, I can say if I pass these images to this artificial neural network with 98% or 90, better to say 97%, with 97% accuracy, it's gonna tell me if the written value, this is a handwriting numbers, with 98%, 97% accuracy, it's able to tell me that what the number is. And maybe we can try a little bit different things. Let's keep this one the way it is, and maybe I can, maybe we can try different activation functions first. Okay, so I remove this one and I want to use the other activation function setup. So I'm going to use the second layer, the first hidden layer. All is going to have now sigmoid, or maybe we can just make it a little bit different. We can say one proportion is sigmoid, the other one proportion is tangent hyperbolic. This means 50% is going to be tangent hyperbolic, 50% is going to be sigmoid. Or if I change this one to this, then 33% is going to be sigmoid and 75% is going to be tangent hyperbolic. Let's just keep it simple like this. Then I need another one. I can say, okay, maybe we can just change this one. I want to say the other one is exactly the same as this one as well, because all these proportions are going to be normalized, so the summation would be 100%. The last layer still is going to keep the activation function of sigmoid. The number of the configs in the first hidden layer or second layer is 2. the number of the configs in the third layer is 2, the number of the configs in the last layer is just 1. So having this model, did it change anything? Let me change. Oh, somehow I copied paste. Oh, what happened? Somehow I screwed the code. Okay. Can I want to just do one more time this previous version I had. I hope I didn't change them before I run the code. Again, the results every time is going to be different because the model is quite large and randomization at the beginning might be you have to run the code multiple times. If you have worked with neural networks, you know what I mean. This is 95% is fine. You can see it's already, there's a probably global minimum here and needs a little bit more epochs. I guess 3 epochs is already fine. I don't need to go for 3 more epochs, but I just leave the code to finish because I want to deallocate the memory which was allocated. You can see already the train validation is, there's the gap between train and validation or test is going bigger. So this is a red flag for me. I would say, okay, the model is being overfitted on trained data set. This is what I don't like to see. But here it was fine. And yeah, 98%, but you have to just think about this. But anyway, I want to do it with another activation setup. I want to forget about this. And now I have this activation set up. And run the code. Let's see what we get. So now you can see 50% of the activation, 50% of the neurons in the first hidden layer or second layer are going to have sigmoid activation function, and the other 50% are going to have tangent hyperbolic. Let's go here. This is the 50% and the other 50%. The same scenario is happening for the second hidden layer or the third layer, and the last one is going to just have the sigmoid. And right now, oh, it's the same. This means that mixed activation function in each layer, not necessarily here, is not going to improve my program. Maybe while this is running, I want to try something else. I want to maybe keep that one to what it is. I just want to use 32 here and then 16 here. This means I just added one more activation function here. I'm going to change this one to one more layer here, and then again I'm going to say this one tangent, the other one also sigmoid. Essentially the number of configs in third layer is third hidden layer or fourth layer is 2. The last one is still gonna be 1. I just need to manually add this one here as well. Again, this is not maybe quite user-friendly to pass the inputs, but you can improve it in the future if you like to change the inputs, the way inputs are given to the program. Do the clean make so now now it's different. I have 5 layers. The one is input. The last one is going to have 16 arrows. The last hidden layer, the middle hidden layer is actually going to have 32 neurons. The number of the trainable parameters is not, it's actually 4,000 less than the previous one. I just increased the number of the hidden, so the neural network is just a little bit deeper, but necessarily doesn't have more trainable parameters. And the accuracy, well, I didn't improve, is quite in the same range. So this architecture is not gonna actually help me. Maybe one thing I can do. We discussed about the linear activation function, what problem it can create, but let's just try it. We'll go back to the first video, the energy efficiency dataset test case study we had. I'm kind of be careful about using linear activation functions as well as value, because we talked about this. When the number is becoming larger and larger in the back propagation, at some point it becomes too much large, and the value, the delta value which is needed to update the weight is become bigger than the double precision limits, and essentially you're going to have NaN values. We had this example in the first video about how to use a scratchANN. So anyway, I'm just going to use maybe just a small proportion, maybe yes, 5. This is good, and then I change this one to 3. Make green. Let's see. So now 20% is going to be value, and the rest, well, I didn't change it all. Well, again, it's kind of the same range. Let's just give it some chance after 2 more epochs. 93%, again, it's the same. So essentially, we can say that this model is capable of predicting the input, the class for the category for the input images with an accuracy around 95%. Something the same we had also in TensorFlow as well. Yeah, I guess that's pretty much everything. I'm just gonna wait until this one also finishes the training for 4 more epochs, which again was not necessary, it's not improving much. One thing you can do, we can just maybe, okay, you know what, I'm going to run one more test case. I'm going to standardize the data, and also because I'm a standardized data, I don't want to divide it by 255 anymore. Let's see. So right now, instead of dividing by 255, I'm just standardizing everything with the standardization function we have. It's the same standardization on Python as well. Oh, it's the same. I'm not gonna bother myself. Anyway, let me know what you think. If you have any questions, feel free to ask below here in the comments. Thank you everyone for watching this video.